Today we're going to talk about limits. Limits is probably a topic that you have not learned about before. This is the first topic for calculus, so it's important that we start it now, since next year is going to go very quickly. What is a limit? You probably don't know yet, but a limit examines what happens at the y value of the function as x approaches a particular number. Now let's talk about how we see that in so far as what it looks like. So this is the standard form for a limit. It says the limit as x approaches the number a of a function f of x equals L. And L has to be a number. We're going to talk a little bit later about how L has to be a number, but we sometimes say it approaches infinity, even though infinity is not a number. Unfortunately, sometimes just plugging the number in doesn't always work. We're going to have to throw every piece of algebra we have at these functions to be able to solve their limits. Sometimes when you plug the function value in, we get an undefined answer, which means we get an indeterminate form. And for us, for right now, an indeterminate form is 0 over 0 or infinity over infinity. We'll talk a lot more about infinities later, but for now, we're just going to focus on 0 over 0, which looks scary, but in actuality, it's going to make us smile because we know we have some way to solve the problem. So I've listed the four main ways that we are going to handle functions and solving their limits here. Factoring will be our first way, polynomial division, which is just a subset of factoring, and then multiplying by the conjugate. Usually when we say conjugate, we talk about either the complex conjugate, you've heard that before, or just the conjugate when we're trying to rationalize a denominator. This time we're not rationalizing a denominator necessarily, we're just trying to work on the undefined part. So we're trying to get that indeterminate form away. So in the one that we've chosen here, we're actually going to be rationalizing the numerator. And then the last way is going to be a common denominator, which is just old school making your fractions talk nicer to each other. So let's take the first way, factoring. Before I do the factoring, my first step is always plugging in. It feels really lame when you've worked so hard to do all this fancy factoring and all you needed to do was plug the function in. So definitely that's always our first step. In this case, we get 4 minus 4 or 0 over 2 minus 2 or 0. So we get an indeterminate form, which makes us very happy because I know there's something I can do. The something I can do for this one is factor. As I can tell, the numerator is the difference of perfect squares, so it'll be x minus 2 and x plus 2 all over x minus 2. Now my x minus 2's will cancel, and I'm just left with the limit as x goes to 2 of x plus 2. Now that I took care of that part that was making it the indeterminate form, I can plug in my 2. So I have 2 plus 2 or 4. So the limit as x goes to 2 of x squared minus 4 over x minus 2 equals 4. So if we were to graph this, this would look like a straight line, but it would have a hole in it. And the way to fill that hole would be by plugging in y equals 4 at x equals 2. So sometimes we're not really able to factor, but what we can do instead is polynomial division. I'm sure you've done polynomial division in Algebra 2. You've done maybe synthetic division and polynomial division. So whichever you feel more comfortable with is what you're going to use whenever you need it. But again, the first thing we always check is that we plug in and see if we even need to do that. So we have 1 cubed minus 4 times 1 plus 3 over 1 minus 1. So let's see, that's 1 minus 4 plus 3. Yep, that's going to be 0, and my denominator will also be 0. So I have this indeterminate form of 0 over 0. And again, that's going to make me happy because I know I can do something to it. Now the something I can do is polynomial division. So let's set that up. X minus 1 into x cubed. Don't forget your placeholder of 0x squared minus 4x plus 3. So x goes into x cubed, x squared times negative 1, negative 1x squared times x is x cubed, and then we subtract. So let's see, the minus will make a plus, so that's going to be x squared. I bring down my 4x. And how do I get x into x squared? Times it by x. So x times negative 1 is negative 1x. X times x is x squared. And then I subtract again. So I have a negative 3x. I bring down my 3 plus 3. And how do I make x into negative 3x? I multiply by negative 3. Negative 3 times 1 is positive 3. Negative 3 times x is negative 3x. And again, I subtract, so I have no remainder. So now my function looks like the limit as x goes to 1 of x squared plus x minus 3. Now this will give me no trouble because I don't have a fraction to make my indeterminate form. So let's just plug straight in. So we're going to get 1 squared plus 1 minus 3, so negative 1. So the limit as x goes to 1 of x cubed minus 4x plus 3 over x minus 1 is negative 1. The next algebraic way we're going to talk about is conjugates. Whenever we have square roots, hopefully you think about rationalizing. Oftentimes you think about rationalizing when you have a square root in your denominator, like 1 over the square root of 2. You'd multiply both the numerator and the denominator by square root of 2. So your answer would be square root of 2 over 2. Other times you have an expression in the denominator that you need to rationalize. So maybe 2 over 3 plus square root of 5. And the way you would rationalize that expression is to multiply by the conjugate. You multiply by 3 minus square root of 5. And maybe you remember that the reason you do that is that you create the difference of perfect squares in the denominator. I'm going to leave the numerator alone just like it is. But in the denominator, I have 3 times 3, which is 9. 3 times minus square root of 5. 3 times positive square root of 5. And then minus square root of 5 squared. So again, I'm going to leave that numerator alone. But my middle terms cancel out, and my denominator is 9 minus 5, or 2 over 3 minus root 5 over 4. And again, I can cancel a little bit more if I wanted to there. We're going to take that exact same concept and apply that to this limit. This limit has we're going to take that exact same concept and apply it to this limit. This limit has the square roots in the numerator. So we're going to be rationalizing the numerator instead of the denominator. But again, our first try is always to see if we even need to do that. So first thing we do is we plug in our 2. So we have the square root of 2 minus the square root of 2 over 2 minus 2, which will definitely be our indeterminate form of 0 over 0. And now I know I can do something with that. In this case, what I can do with that is multiply the numerator and the denominator by the conjugate of the numerator. So it'll be the limit as x goes to 2, and then we have minus x minus root 2, and the conjugate will be minus x plus root 2 over x minus 2, and again, whatever I do to the numerator, I have to do to the denominator. So we have root x plus root 2. And just as you saw in the Algebra 2 example off to the right, we're not going to bother touching with the part that doesn't include the square roots. We're only going to multiply out the part that we've made now to be a difference of perfect squares. So the limit as x goes to 2, we have root x times root x, which is just x, positive square root of x times square root of 2, and negative square root of x times square root of 2, and those will cancel. And then root 2 times root 2 is minus 2. That becomes my numerator, and my denominator is x minus 2 over root x plus root 2. And here I see that I get to cancel. I get to cancel out the thing that was making me have an indeterminate form. So I'm left with the 1 in the numerator, and I have the limit as x goes to 2 of 1 over root x plus 2, which is 1 over root 2. Root 2 plus root 2, which is 1 over 2 root 2. You're welcome to rationalize that and get the square root out of the denominator if you want, but it's not necessary in calculus. Our last type of algebra that we're going to be dealing with today is making common denominators. Just old school common denominators that you've been doing since 3rd grade. We're just going to take it up a notch and put it into calculus. So again, our first step is to always plug in. Let's see if we even need to do this. So we have 1 over 0 minus 1 over 0 squared plus 0. Oh, that looks very scary. We're going to get 1 over 0, which again, I know I might be able to do something with it. This undefined term, we're going to try and figure out something to do with it. In this case, what we're going to do with it is make a common denominator. Before I make my common denominator, I'm going to factor the second fraction so it looks a little bit nicer to play with. So it'll be x times x plus 1. And now I see that both of my fractions have x's in them. So I don't need to worry about the x. What I do need is to multiply the first one by x plus 1. And remember, whatever I do to the numerator, I have to do the denominator. So it will be the limit as x goes to 0 of 1 times x plus 1 over x times x plus 1 minus 1 over x times x plus 1. Now that I have a common denominator, I can combine my numerators. So it'll be the limit as x goes to 0 of x plus 1 minus 1 over x times x plus 1. Now my minus 1 and my plus 1 will cancel. So I get the limit as x goes to 0 of x over x times x plus 1. And look at what happens now. I'm able to cancel my x in my numerator and my x in my denominator, and I'm left with a 1 in the numerator. So I have the limit as x goes to 0 of 1 over x plus 1. So now I can plug in my 0, and I get 1 over 0 plus 1, which is just 1. So the limit of that very messy looking fraction in the beginning is just a really simple number of 1.